Reality is not what it seems. The universe is built upon a fabric called space-time, and its true nature defies our everyday experience. We are about to journey through 30 astonishing facts that will fundamentally alter how you perceive everything, from the force of gravity to the very flow of time itself. You will discover how time can slow down, how empty space is alive with energy, and whether the past and future might already be written. By the end, you will see the cosmos not as a collection of separate objects, but as a single, dynamic tapestry where the rules of physics are rewritten. How do you think your reality would change if you could see this hidden fabric all around you? Our universe runs on a single, unified fabric. We used to think of space as the empty stage where events unfold, and time as the universal clock ticking away in the background. But Einstein revealed that this is a profound illusion. Space and time are not separate. They are intimately woven together into a single entity, a four-dimensional continuum we call space-time. Think of it like a piece of cloth. You cannot have the length of the cloth without its width. The two are inseparable aspects of the whole. In the same way, you cannot have space without time. Every event in the cosmos is pinpointed not just by its three spatial coordinates, where it is, but also by its position in time when it happens. This is the foundational idea of Einstein's theory of relativity. This interweaving is not just a philosophical concept, it is the very mechanism behind the force of gravity. A massive object like the Sun does not simply pull on the Earth. Instead, it warps the fabric of space-time around it, and the Earth follows the curved path created by that warp. Without this four-dimensional framework, the true structure of the universe, from the orbits of planets to the bending of light, would remain a complete mystery. This revolutionary idea completely redefines the pull you feel from the Earth. Gravity, in Einstein's universe, is not a mysterious force reaching across space. It is a geometric effect, a direct consequence of mass and energy telling space-time how to curve. The more massive an object is, the deeper the dent it creates in this cosmic fabric. A perfect way to visualize this is to think of a stretched rubber sheet representing the fabric of space-time. If you place a heavy bowling ball in the center, the sheet stretches and curves dramatically around it. Now roll a marble across this warped sheet. The marble will not travel in a straight line, it will spiral inward, tracing a path around the central depression. The marble is not being pulled by a force from the bowling ball, it is simply following the curved geometry of the sheet itself. Our solar system operates on this exact principle. The Sun is that massive bowling ball, creating a profound curvature in the space-time around it. The Earth, along with all the other planets, is like that marble, following the invisible grooves of this curvature in what we perceive as our stable orbit. We are not being pulled, we are constantly falling along a path dictated by the shape of the universe itself. This geometric nature of gravity has been confirmed in spectacular ways. Light itself, which has no mass, bends as it travels through curved space-time near a massive star, a prediction Einstein made that was later proven during a solar eclipse. So the next time you drop your keys, remember they are not being pulled down by a force. They are simply following the straightest possible path through the curved space-time created by our planet. This single concept connects the fall of an apple to the motion of distant galaxies. This geometric curvature of space-time has a startling consequence for time itself. Time does not flow at a single, universal rate. It is a local phenomenon, and its passage depends entirely on your speed and your proximity to gravity. This effect, known as time dilation, is not science fiction. It is a measurable, everyday reality. Consider the network of global positioning system satellites orbiting high above our planet. These satellites carry incredibly precise atomic clocks. According to Einstein's theory, two things affect their clocks. First, because they are moving at high velocities relative to the Earth, their clocks should run slower. But second, because they are farther from Earth's gravitational pull, their clocks should run faster. In this case, the gravitational effect wins out. The clocks on the satellites actually tick faster than identical clocks on the ground. If engineers did not deliberately correct for this, the entire GPS system would accumulate errors of several miles within a single day. Your phone's navigation would be useless. This proves that time dilation is not just a theoretical quirk, it is an essential factor for modern technology to function. This phenomenon was confirmed in a famous experiment back in 1971. Scientists flew atomic clocks on commercial airplanes around the world. When they compared these traveling clocks to stationary ones on the ground, they found a tiny but undeniable difference. Time on the fast-moving airplanes had passed ever so slightly slower. For the passengers, the flight lasted a few hours. For their clocks, the journey was a fraction of a second shorter. This is the universe's true nature. Your clock and a clock on a speeding rocket will never agree because time itself is woven into the flexible fabric of space-time. So the next time you check a map on your phone, remember you are relying on a theory that fundamentally rewrites our understanding of time. This universal speed limit has a profound effect on the very structure of causality. Because nothing can outpace a light beam, the order of cause and effect becomes a sacred rule woven into the fabric of space-time. An event here cannot possibly influence an event over there faster than light could travel between them. This cosmic speed limit ensures that the past cannot be changed from the present, preserving a logical sequence of events across the universe. If you could somehow send a message faster than light, you could theoretically send it back in time, creating bewildering paradoxes where an effect could precede its own cause. The universe, it seems, is built to prevent such logical nightmares from ever occurring. This limit also leads to some truly bizarre consequences for any object attempting to approach light speed. As an object moves faster and faster, its energy increases, but it does not just increase a little, it increases dramatically. To push the object closer to that ultimate speed limit requires ever more astronomical amounts of energy. According to the equations of relativity, as the object's speed approaches the speed of light, its mass, or more precisely its inertial resistance, effectively becomes infinite. To actually reach the speed of light would therefore require an infinite amount of energy, which is an obvious impossibility. This is why no object with mass can ever achieve that final velocity. The speed of light is not just a barrier, it is a fundamental property of reality that shapes everything from the smallest particles to the grandest cosmic structures. It is the constant that defines the relationship between space and time, energy and matter. Every time you see a distant star, you are witnessing light that has traveled for years, even centuries, to reach your eyes, faithfully obeying this cosmic rule. That simple beam of starlight is a messenger from the past, carrying information at the only speed the universe allows. This ultimate speed limit of light leads us directly to the most extreme objects in the cosmos. If mass warps the fabric of space-time, then a black hole is a place where that fabric has been torn apart by its own weight. A black hole is not a hole in the sense of an empty void. It is an almost unimaginable concentration of mass crushed into a point of infinite density called a singularity. The gravitational pull of this singularity is so powerful that it curves space-time into a bottomless pit. Surrounding this singularity is the boundary we call the event horizon. Think of the event horizon not as a physical surface, but as a point of no return, a one-way gate in the universe. Once any object, even a particle of light, crosses this invisible threshold, it can never come back out. The escape velocity required to break free from within the event horizon would need to be greater than the speed of light. And since nothing can achieve that, the fate of anything that crosses is sealed. The laws of physics as we know them break down at this point, but the journey toward the singularity is even more bizarre than simply disappearing. Imagine an astronaut unfortunate enough to fall feet first toward a black hole. The pull of gravity on their feet would be vastly stronger than the pull on their head because their feet are closer to the immense mass. This difference in gravitational force, known as a tidal force, would stretch their body lengthwise into a long, thin stream of atoms. At the same time, the sides of their body would be compressed inward. This violent process has a fittingly vivid name, spaghettification. Any object, be it a star, a spacecraft, or a cloud of gas, would be shredded into a thread of elementary particles before it even reached the center. A black hole is the ultimate expression of gravity's power, a region where the warping of space-time becomes so severe that it creates a permanent prison from which not even information can escape. Yet the very equations that predict these gravitational prisons also hint at a possible escape route. Einstein's field equations, the mathematical heart of general relativity, contain solutions that describe tunnels through the folded fabric of space-time. These theoretical passages are known as wormholes. Picture the universe not as a flat sheet, but as a vast, crumpled piece of paper. 2 points that are very far apart on a straight line could be brought almost together by folding the paper. A wormhole would be a tiny bridge, a shortcut connecting those two distant locations instantly. In theory, you could step into one end of this tunnel and emerge 1,000,000 light-years away in a fraction of a second, effectively traveling faster than light by not moving through normal space at all. The most famous of these theoretical models is the Einstein-Rosen bridge, a structure that mathematically connects two separate points in space-time. This is not mere fantasy, it is a genuine, if highly speculative, possibility allowed by the same laws that govern black holes. However, finding a wormhole and actually using it are two very different challenges. The primary problem is stability. The passages predicted by pure mathematics are incredibly fragile. They would tend to collapse into a singularity the instant anything, even a single photon of light, tried to pass through. To keep a wormhole open and traversable, you would need a form of exotic matter. This is not matter as we know it. Exotic matter would have to possess negative energy density, effectively pushing the walls of the wormhole apart and preventing its violent collapse. Whether such matter can exist in sufficient quantities is one of the great unanswered questions in theoretical physics. Science fiction has long embraced the idea of wormholes as convenient portals for interstellar travel, but the reality would be far more precarious. Even if one were discovered and stabilized, the journey through it would be unlike anything we can experience. The intense gravitational forces and the warping of space and time within the tunnel could have unpredictable effects. Could a wormhole also connect two different points in time, or even bridge two entirely separate universes? The mathematics does not rule it out. For now, these cosmic shortcuts remain a breathtaking glimpse into the profound possibilities hidden within Einstein's universe, a reminder that the fabric of reality may be far more connected and far stranger than it appears. The very fabric of space-time is not a static stage. It is dynamically stretching on the grandest of scales. Edwin Hubble made the monumental discovery in the 1920s that distant galaxies are all rushing away from us, and the farther away they are, the faster they recede. This was not a sign that we occupy a special, central location in the cosmos. Instead, it revealed a profound truth: the universe itself is expanding. The space between galaxies is literally stretching, carrying them apart like raisins in a rising loaf of bread. This observation was the first major piece of evidence for the Big Bang theory, the idea that our entire universe began from an immensely hot, dense state nearly 14 billion years ago. Since that initial moment, space-time has been expanding and cooling, allowing for the formation of all the stars and galaxies we see today. But the story does not end there. In the late 1990s, astronomers made an even more startling discovery. They found that this cosmic expansion is not slowing down due to gravity, as everyone had expected. It is actually speeding up. Something is pushing the galaxies apart with ever-increasing force. This mysterious something is what we call dark energy. Dark energy is not a substance you can touch or see. It appears to be a property of space itself, a kind of repulsive gravity that permeates the vacuum of space-time and causes it to stretch at an accelerating rate. This is the dominant force shaping the ultimate fate of our cosmos, yet we have almost no idea what it truly is. It remains one of the greatest unsolved mysteries in all of physics. How will this relentless acceleration reshape the universe in the distant future? While a black hole is a one-way journey, time travel into the future is a proven, one-way ticket already available in the universe. You would not need a mysterious portal or a futuristic machine, just a very fast spaceship. Einstein's time dilation makes this possible. If you were to embark on a journey through space at a significant fraction of the speed of light, a strange thing would happen. For you, time would pass normally. You would eat your meals, read a book, and feel the years go by. But when you finally returned to Earth, you would find that everyone you knew had aged far more than you. You would have effectively jumped into their future. This is not a guess, it is a direct consequence of the laws of physics. The faster you move through space, the slower you move through time relative to someone who is stationary. This leads to one of the most famous thought experiments in all of science, the twin paradox. Imagine a pair of identical twins. One remains on Earth while the other boards a rocket and travels to a distant star at near light speed. From the Earth twins' perspective, the clock on the speeding rocket appears to tick agonizingly slowly. When the traveling twin finally returns home, they step out of their ship looking only a few years older. They are greeted by their Earth-bound sibling, who is now an old man or woman. The paradox is not that time dilation happened, but in understanding why the traveling twin is the one who aged less. The answer lies in acceleration. The twin on the rocket had to turn around to come home, and that change in motion is absolute. It breaks the symmetry between the two, confirming that the traveling twin truly experienced a different, slower passage of time. This has been verified with incredible precision. Those atomic clocks flown on airplanes were, in a very real sense, time travelers. They returned to the lab having experienced a few billionths of a second less than the clocks that stayed behind. Scale that up to a journey near a black hole or at near light speed, and the effect becomes dramatic. You could leave Earth today, take a circuitous route for what feels like a decade, and return to find 1,000 years have passed. You would be a relic from the past, stepping into a world you no longer recognize. This is not science fiction, it is the universe's own rulebook. The future is a destination you can reach simply by moving fast enough. But if time is so flexible, what if it is not flowing at all? The block universe theory proposes a truly radical idea. The past, present, and future are not successive states. They all exist simultaneously, fixed forever within a four-dimensional structure. In this view, the entire history of the cosmos, from the Big Bang to the farthest future, is already written. Your birth, your life, and every event yet to come are all equally real, just as real as Paris is to London. We do not move through time, we simply experience different parts of this eternal block. This is not a mystical concept, it emerges directly from Einstein's own equations of relativity. In his theory, there is no universal now. Two events that are simultaneous for one observer may happen at different times for another moving observer. This shatters the idea of a single, progressing present moment for the entire universe. Our powerful feeling that time flows, that the future is open and the past is gone, might be nothing more than a stubborn illusion of our conscious minds. Think of the entire universe as a finished movie on a DVD. The film contains every scene from the opening credits to the final shot. When you watch it, you experience a sequence of events, a flow from beginning to end. But the entire movie, all 120 minutes of it, exists completely on the disc. Your consciousness is simply the laser reading one frame after another, creating the sensation of a moving present. In the block universe, reality is that complete DVD. We are not the audience watching the film, we are characters within it, experiencing our personal timeline one frame at a time. This means that your future self, in a very real sense, is already out there. The moment you are reading this sentence, the moment you first learn to ride a bike, and the moment you will take your last breath, all persist together in the vast, unchanging geometry of space-time. This idea challenges our deepest intuitions about free will and destiny. Are we truly making choices, or are we just following a path that has always been there, a groove in the cosmic record that we cannot see beyond our current note? The block universe does not provide easy answers, but it forces us to confront the possibility that the river of time is an ocean, and we are merely sailing a predetermined course across its timeless surface. This notion of a fixed, four-dimensional block of reality might seem to leave no room for randomness, yet at the tiniest scales, the universe is anything but still and certain. Empty space is a misnomer. The vacuum of space is not a void but a seething, bubbling sea of activity governed by the bizarre rules of quantum mechanics. At the Planck scale, distances so small they are almost meaningless to our everyday experience. A process called quantum fluctuation is constantly occurring. The Heisenberg uncertainty principle dictates that for incredibly brief moments, energy can be borrowed from nowhere, allowing pairs of virtual particles and antiparticles to spontaneously pop into existence. These are not full-fledged particles in the way we normally think of them. They are ghostly apparitions, a particle and its antimatter counterpart emerging together from the fabric of empty space. They exist for a fleeting instant, just long enough to satisfy the universe's quantum ledger, and then they annihilate each other, vanishing back into the nothingness from which they came. This is not a theoretical fantasy. We can observe the effects of this quantum frenzy. If you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they will experience a faint, attractive force pushing them together. This is the Casimir effect. Why does this happen? In the empty space between the plates, only certain wavelengths of these virtual particles can flicker into being. But outside the plates, all wavelengths are possible. The greater pressure from the particles outside pushes the plates inward. The void itself is exerting a force. This ceaseless creation and destruction has a profound implication for space-time itself. Each of these quantum events is a tiny tremor in the cosmic fabric. Space-time at this fundamental level is not smooth and serene. It is a chaotic foam, a storm of random, microscopic fluctuations where the very concepts of distance and duration break down and become fuzzy. This quantum foam is the absolute bedrock of reality, suggesting that the seemingly solid stage upon which the universe plays out is at its heart a turbulent and probabilistic sea. The violent churn of the quantum foam hints at a universe in constant motion, and sometimes that motion creates literal waves in reality itself. Gravitational waves are not waves of matter or energy in the traditional sense. They are ripples in the very curvature of space-time, stretching and squeezing the fabric of the cosmos as they travel outward. Picture the universe as a calm, still pond. If you toss a pebble into the center, circular ripples spread across the surface, making floating leaves bob up and down. Now imagine that the pond itself is the three-dimensional fabric of space, and the pebbles are the most violent events imaginable. When two immense objects like black holes spiral into each other, they do not just collide quietly. Their final death dance sends violent shudders through space-time, propagating outward as gravitational waves at the speed of light. These waves compress space in one direction while stretching it in the perpendicular direction, effectively changing the distance between objects as they pass through. For decades, these waves were purely theoretical, a key prediction of Einstein's theory that even he doubted we could ever detect. The distortion they cause is incredibly tiny, far smaller than the width of a single atom. But in September 2015, humanity finally succeeded. the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct observation. The signal came from a pair of black holes, each about 30 times the mass of our Sun, that had been orbiting each other in a final, frantic spiral over 1 billion light-years away. Their cataclysmic merger, releasing more power in a fraction of a second than all the stars in the observable universe combined, created a gravitational wave that rang through the cosmos like a bell. By the time it reached Earth, the wave had faded to a whisper, stretching and squeezing our planet by a minuscule amount. LIGO incredibly sensitive detectors with laser beams traveling down 4-kilometer-long vacuum tubes measured this infinitesimal change in length. That single chirp, a brief upward sweep in frequency, confirmed a century-old prediction and opened an entirely new window on the universe. We are no longer limited to observing the cosmos through light alone. We can now listen to the vibrations of space-time itself, hearing the echoes of collisions that are completely invisible to telescopes. Each new detection tells us about the hidden population of black holes and neutron stars, revealing the dynamics of these extreme objects and testing the very limits of general relativity. Every ripple carries a story of a cosmic catastrophe, a message from the warped heart of gravity. The ripples from those cosmic collisions carry us back to the very origin of everything, to a moment when time itself may have been born. If the universe is expanding, then rewinding the cosmic film takes all the galaxies back to a single, unimaginable point of infinite density and temperature, the Big Bang. This was not an explosion in space, but the violent emergence of space and time themselves. The singularity at the beginning poses one of the most profound challenges to physics, because at that point our current laws break down completely. The equations of general relativity simply stop working. In that state of infinite curvature, the very concepts of before and after lose all meaning. Asking what happened before the Big Bang might be as nonsensical as asking what is north of the North Pole. There is no before because time, as a dimension we can measure, did not exist. The beginning of the universe was the beginning of time. From that singular state, the fabric of space-time unfurled, and in the first fleeting fractions of a second, the fundamental forces that govern our reality froze out from a unified superforce. Gravity peeled away first, then the strong nuclear force, followed by the weak and electromagnetic forces. This cosmic phase transition set the stage for everything to come, for the formation of quarks, atoms, and eventually us. The emergence of these laws from a state of pure symmetry is like watching water vapor crystallize into a unique, complex snowflake. The universe chose one set of rules from an infinite number of possibilities, and that single choice determined the nature of stars, planets, and life. Contemplating a beginning with no prior cause forces us to confront the ultimate mystery. Did time simply switch on, or is our entire cosmic history just one bubble in a much vaster, timeless multiverse where beginnings are commonplace? For now, the origin of time remains the deepest horizon of our understanding, a moment where physics meets philosophy at the edge of existence. Einstein's field equations are the silent architects of our cosmos. They translate the simple presence of mass and energy into the complex geometry of the universe. The relationship is a two-way street, an elegant dialogue written into the fabric of reality. On one side, the equations declare that mass and energy tell space-time how to curve. Anything that has mass or energy, from a planet to a beam of light, creates a depression in the four-dimensional fabric. On the other side, this newly curved space-time tells that same mass and energy how to move. Objects do not travel in straight lines out of sheer will. They simply follow the most natural path available through the warped landscape, a path we call a geodesic. This cosmic conversation explains why an apple falls and why planets orbit, but its most stunning confirmation came from something massless, light itself. Einstein predicted that the path of a light beam would also bend when passing through curved space-time, particularly near a massive object like our Sun. He calculated that starlight grazing the sun's surface would be deflected by a tiny but measurable angle. Proving this required a celestial alignment, a total solar eclipse, to blot out the sun's overwhelming glare and make the faint background stars visible. In 1919, expeditions led by Arthur Eddington traveled to Africa and Brazil to photograph the Hyades star cluster during the eclipse. When they compared the stars' positions to their normal locations in the night sky, the measurements revealed a shift. The starlight had been bent exactly as Einstein's equations had foretold. This was not a force tugging on the photons, it was the sun's mass curving the space through which the light traveled, forcing it to follow a new, arched path. That single observation during a few minutes of darkness catapulted Einstein to global fame and cemented a new picture of the universe. Every time you see a star twinkle, remember its light may have traveled a curved road to reach you, a silent testament to the invisible geometry that guides all motion. There is another, equally strange consequence of approaching that universal speed limit. Just as time stretches, space itself compresses. An object racing toward you at a significant fraction of light speed would not just have its clock running slow, it would also appear physically shorter in its direction of travel. This phenomenon is known as length contraction. If you could see a spaceship traveling past at 90% of light speed, it would look as though it had been squashed like a car in a compactor. This is not an optical illusion or a trick of the light. It is a real physical contraction of space as measured by a stationary observer. The faster the object moves, the more severely its length contracts. At 87% of light speed, its length would be halved. At 99.5%, it would be just 1/10 of its original length. This bizarre effect is the essential counterpart to time dilation, and both are required to uphold the most fundamental rule in the universe, the constant speed of light. Imagine you are on a train moving at half the speed of light, and you turn on a flashlight pointing forward. According to classical physics, the light from your flashlight should be traveling at light speed plus the speed of the train. But Einstein's universe does not allow that. Every observer, whether they are on the moving train or standing on the platform, must measure the exact same speed for that beam of light. How is this possible? Time dilation and length contraction work together like cosmic accountants, balancing the books to keep the speed of light constant. For the person on the platform, the clock on the fast-moving train is ticking slower, and the train itself is physically shorter. These two distortions perfectly adjust the measurements of time and distance so that when they calculate the speed of the light beam from the train, it always comes out to the same immutable number. This means that the very fabric of space is not rigid, it is flexible and personal. Your measurement of an object's length depends entirely on your state of motion relative to it. A meter stick flying past you at high speed is genuinely shorter than the identical meter stick resting in your hand. The universe ensures its most fundamental constant remains unwavering by warping the very dimensions of space and time around anything that moves. So the next time you see a shooting star streak across the sky, consider that from its own perspective, its incredible journey was even shorter than it appeared to you. Our experience of time's relentless forward march is deeply tied to a concept of increasing disorder. Why do we remember the past but not the future? Why does a shattered glass never spontaneously reassemble itself? The answer lies in a fundamental law of physics called the second law of thermodynamics. It states that the total entropy, which is a measure of disorder or randomness in a closed system, always increases over time. Think of a brand new deck of cards fresh from the box. The cards are in perfect sequential order, a state of very low entropy. Now shuffle that deck thoroughly. The cards become randomized, a state of high entropy. The journey from order to disorder is easy and natural, but reversing the process, getting the deck back into its original sequence by simply shaking it, is so statistically improbable that it is effectively impossible. This is the essence of the arrow of time. The universe as a whole is like that deck of cards. It began in an incredibly ordered, low-entropy state at the Big Bang, a condition of exquisite uniformity and simplicity. Ever since that initial moment, the cosmos has been shuffling itself, evolving toward greater and greater disorder. Stars burn out, galaxies disperse, and energy spreads thin. This cosmic trend toward disorder is what gives time its direction. It is the reason we perceive a clear difference between the past, which was more ordered, and the future, which will be more disordered. Without this universal increase in entropy, there would be no inherent difference between one moment and the next, and the flow of time would lose all meaning. Our very consciousness, our ability to form memories and make plans, is a process that consumes energy and generates waste heat, contributing to the universal rise in entropy. We are not just observers of time's arrow, we are participants in its flight, living proof of the universe's one-way journey from order to chaos. This cosmic arrow of time, pointing from order to chaos, relies on a smooth and continuous space-time for its journey. But what if the fabric itself is not smooth at all? What if, when you zoom in far enough, reality reveals a grainy, pixelated structure, like a cosmic photograph enlarged until it breaks into individual dots? This is the startling possibility that emerges when we push our theories to their absolute limits. At the incredibly tiny Planck scale, a distance of 10 to the negative 35 meters, the smooth continuum described by Einstein might dissolve into a fundamental grain. Space-time could be composed of discrete, indivisible units, a finite number of building blocks that make up the universe, much like a digital image is made of pixels. This idea of a granular reality is the heart of theories like loop quantum gravity, which seeks to solve the greatest conflict in modern physics. Einstein's general relativity gives us a magnificent picture of the cosmos on large scales, where space-time is a flexible fabric. But quantum mechanics governs the wild, probabilistic world of the very small. The two theories are spectacularly successful in their own domains, but they are fundamentally incompatible. They speak different mathematical languages and make contradictory claims about the nature of reality, particularly at the center of a black hole or the moment of the Big Bang, where both immense gravity and tiny quantum scales meet. General relativity says space-time is smooth and continuous, while quantum mechanics demands that everything, including fields and energy, comes in discrete quantized packets. So how can space-time itself be an exception? Loop quantum gravity proposes a radical answer. It suggests that space is not a background stage but a dynamic network of relationships. Imagine a spiderweb where the threads represent the fundamental quanta of space. The web is not sitting in space, the threads and their connections are space. These tiny loops of gravitational field woven together form the fabric of the cosmos. In this view, the volume of a region and the area of its surface are not continuous values that can be any size. They are quantized, meaning they can only take on specific, discrete values, much like the energy levels of an atom. You cannot have half a unit of space, just as you cannot have half an electron. This granular structure becomes apparent only at the Planck scale, which is why our everyday world feels so seamless. The transition from a smooth fabric to a granular one is like walking away from a giant tapestry. From a distance, the image is continuous and fluid, but up close you see the individual threads that weave it together. The universe operates in the same way. This pixelation of reality could have profound implications. It might provide a natural cutoff that prevents the infinities that plague theories of quantum gravity, offering a way to understand the Big Bang singularity not as an infinite point, but as a quantum bounce from a previous universe. The very smoothness of space-time that allows time's arrow to fly might be an emergent illusion, a collective effect of countless tiny grains vibrating in harmony. The very threads of space-time may have tangled and knotted as the universe first cooled. Cosmic strings are hypothetical relics from that primordial chaos, unimaginably thin cracks frozen into the fabric of reality moments after the Big Bang. Think of them as one-dimensional scars, thinner than a single atom but stretching across the entire cosmos for light years. Their true nature is one of density, packing the mass of entire mountains into every centimeter of their length. This creates a gravitational presence so extreme that a cosmic string would warp the space around it into a perfect, razor-sharp cone. If one were to pass silently between you and a distant star, you would not see one star, but two identical copies of it, split by the string's incredible gravitational lensing. The string itself would be invisible, a flaw in reality acting like a perfect prism for starlight, but the strangest consequence lies in the geometry of this warping. The space around a cosmic string is not simply curved, it is torn and stitched back together in a way that fundamentally alters the rules of travel. Because the string removes a slender wedge of space from the cosmic circle, the angles of a triangle drawn around it would not add up to 180 degrees. This bizarre topology could, in theory, create a path to the past. If two strings were moving relative to each other at near light speed, the space around them could form a closed time-like curve. An object following a precise trajectory around these dancing strings could, according to the mathematics, return to its starting point in space before it ever left, effectively traveling backward in time. While no cosmic string has ever been confirmed, their potential existence reminds us that the early universe may have left behind more than just stars and galaxies. It might have left cracks in the very foundations of reality where the normal flow of cause and effect breaks down completely. Even your head is older than your feet. This is the bizarre reality of gravitational time dilation, a direct consequence of living in a warped space-time. The force of gravity does not just pull on objects, it pulls on time itself, slowing its passage wherever the gravitational field is strongest. This means that time runs measurably faster the farther you are from a source of gravity. A clock placed on a mountaintop where Earth's pull is ever so slightly weaker will tick faster than an identical clock at sea level. The difference is incredibly small. Just a few nanoseconds gained over a lifetime for someone living on a high floor of a skyscraper, but it is undeniably real. This effect has been confirmed with astonishing precision using atomic clocks. Scientists have synchronized two ultra-precise clocks and then lifted one just a few feet above the other. The elevated clock consistently runs faster, gaining a tiny fraction of a second compared to its partner on the ground. This is not a mechanical error, it is the universe operating exactly as Einstein predicted. The very fabric of time is stretched thinner by gravity, so your feet are literally experiencing a slightly slower, more dragged-out version of time than your head. This phenomenon forces engineers to make constant corrections in our most advanced technologies. The Global Positioning System is a perfect example. The satellites are in a much weaker gravitational field high above the Earth, causing their onboard atomic clocks to run faster than those on the ground. If this effect were not programmed into the system, the GPS coordinates your phone provides would drift by several miles in a single day, rendering navigation useless. Every time you use a Maps app to find a coffee shop, you are relying on our understanding of this subtle warping of time. It is a silent, invisible force that shapes our modern world, a constant reminder that the flow of time is not a universal constant but a personal experience, intimately tied to your position in the gravitational landscape of the cosmos. These points of infinite curvature are known as singularities. They are not just extreme locations, they are the absolute edge of the map, the final frontier where the fabric of space-time itself is torn apart by its own geometry. At the heart of every black hole, according to our best equations, lies a singularity. This is the point where the star's entire mass has been crushed into a volume of zero size, resulting in infinite density and an infinitely deep warp in space-time. The gravitational pull becomes so overwhelming that the very paths through space and time converge on this one point. every future direction for anything that crosses the event horizon leads inexorably to its own destruction at the singularity. The rules of physics as we know them, the very language of cause and effect, cease to function here. The same is true for the very beginning of our universe. The Big Bang started from a singularity, a state of infinite temperature and density where the concepts of before and after have no meaning. These singularities are not objects you can touch or see. They are mathematical warnings that our current theories have reached their breaking point. They scream that a deeper, more complete theory of quantum gravity is needed to describe what truly happens when space-time is stretched to its absolute limit. The smooth, curving fabric of general relativity cannot cope with such infinite extremes. It is like using the physics of water waves to describe what happens at the exact center of a maelstrom where the water vanishes into a dimensionless point. The equations simply output infinity, which in physics is a clear sign that you are missing a crucial piece of the puzzle. What truly exists at the center of a black hole, or in the first moment of creation, remains one of the greatest mysteries. Is the singularity a real, physical point of infinite warping, or is it merely a placeholder, a sign that our current mathematics fails to capture a more complex quantum reality where space and time are fundamentally granular? The search for an answer is a journey to the very limits of reality, where the familiar fabric of the cosmos frays into the unknown. This division of space-time into possible and impossible connections is mapped by a structure called the light cone. Picture a single, fleeting event like the flash of a spark in the vast darkness. From that spark, light expands outward in all directions at, of course, the speed of light. Over time, this expanding sphere of light paints a four-dimensional shape in space-time, a cone whose tip is the original event. This is your light cone, and it defines the entire causal universe for that single spark. The interior of the cone, reaching backward into the past, contains every event that could have possibly sent a signal, any signal, to reach that spark at the moment it flashed. It is the entire history of the universe that is relevant to that event. Conversely, the interior of the cone reaching forward into the future contains every event that the spark could ever possibly hope to influence. Any place its light or any slower message could ever reach, but here is the crucial part. Everything outside that double cone is forever disconnected. Events out there are in a region called elsewhere. They cannot affect your spark, and your spark cannot affect them, because to do so would require communicating faster than light, breaking the universe's fundamental speed limit. This is not just a diagram, it is the absolute law of cause and effect. Your entire life, from your perspective right now, sits at the tip of your own personal past light cone. Every sight you have ever seen, every sound you have ever heard, every person who has ever touched your life, all of that information has traveled to you from within your past light cone at the speed of light or slower. And every action you take, every word you speak, ripples out from you into your future light cone, defining the entire sphere of your potential influence on the cosmos. This structure makes the universe both vast and intimately personal. You are causally connected to a specific, finite slice of reality, a bubble of influence that expands at the speed of light from your birth to your death. The star that exploded 1,000,000 years ago, 1,000,000 light years away, its light is only just reaching you now, so it is inside your past light cone. But a cataclysmic explosion happening right now in a galaxy 1,000,000 light years away is outside your cone, in the absolute elsewhere. You are blissfully unaware and will be for 1,000,000 years, because that information cannot possibly reach you any faster. The light cone is the ultimate arbiter of reality, drawing a stark, geometric line between what is possible and what is forbidden in the cosmic fabric. The ultimate destiny of everything you see is written in the invisible geometry of the cosmos. The overall shape of space-time itself, whether it curves back on itself like a sphere, bends away like a saddle, or remains perfectly flat, dictates the final chapter of the universe. This geometry is not an abstract concept, it is a direct measure of the total density of all the energy and matter in existence. If the density is high enough, the gravitational pull will eventually halt the expansion and pull everything back together in a fiery big crunch, a closed universe. If the density is too low, gravity loses its grip, and the universe will expand forever into a cold, dark emptiness, an open universe. But our most precise measurements from satellites mapping the faint afterglow of the Big Bang point to a third, seemingly perfect possibility. The universe appears to be geometrically flat, balanced on a razor's edge between these two extremes. This flatness suggests a specific, critical density where the expansion will continue forever, but will slow to a crawl over trillions of years. In this future, the relentless work of dark energy ensures that galaxies beyond our local group will eventually fade from view, their light stretched to undetectable wavelengths as space itself stretches. Stars will burn out, black holes will slowly evaporate, and over near infinite time, the universe will approach a state of maximum entropy, a uniform, frigid sea of diluted particles where no more work can be done. This is the heat death, the final equilibrium where the cosmic story simply runs out of energy to write new events. The flat geometry of our space-time does not lead to a dramatic collapse, but to a slow, quiet fade, a testament to the profound connection between the shape of reality and the fate of all it contains. A spinning planet does far more than just warp the space around it. It actively grabs hold of the fabric and twists it into a vortex. This phenomenon, known as frame dragging or the lens-thirring effect, reveals that space-time is not a passive backdrop but a dynamic fluid. Just as a spinning spoon stirs honey, pulling the liquid around with it, a massive rotating object like Earth drags the local frame of space-time in the direction of its rotation. The effect is incredibly subtle for our planet, but according to Einstein's theory, it must be there, a faint whirlpool in the invisible structure of reality encircling our world. Proving this required one of the most precise experiments ever conceived. The Gravity Probe B satellite was launched with a singular, elegant mission. Inside its sleek body were 4 of the most perfect gyroscopes ever built, spheres of quartz so impeccably smooth that if they were enlarged to the size of the Earth, their tallest mountain would be just a few feet high. These spheres were spun up and set adrift in a near-perfect vacuum, their spin axes pointed at a distant guide star. If space was merely static, as Newton believed, those gyroscopes would have held their alignment forever. But if Einstein was right and frame dragging was real, the gentle tug of Earth's rotating space-time would very slowly pull the gyroscope's axis out of alignment. For over a year, the satellite collected data, measuring a drift so minuscule it is equivalent to watching the width of a human hair from over 200 miles away. The result was a triumphant confirmation. The fabric of space-time itself was being dragged around our planet exactly as predicted. Now, amplify this effect from a planet to a black hole. A spinning black hole, or Kerr black hole, doesn't just create a gravitational pit. It creates a maelstrom of whirling space-time around its event horizon, and region called the ergosphere. Within this region, nothing can remain stationary. Everything is forced to move in the direction of the spin, a cosmic riptide so powerful it could theoretically be used to extract energy from the black hole itself. Frame dragging shows us that gravity is not just a curvature, it is a current, and every spinning object in the universe, from a humble planet to a colossal black hole, pulls the cosmic fabric along for the ride. Yet this cosmic fabric, with its strict light cones and speed limits, faces a bizarre rebellion at the smallest of scales. Quantum entanglement presents a paradox that seems to shred the rulebook of local space-time. 2 particles can become intimately linked, their fates intertwined in a way that defies our classical intuition. Once entangled, the measurement of one particle's property, like its spin, will instantly determine the property of its partner, even if that partner is now on the opposite side of the galaxy. There is no signal traveling through space, no ripple in the gravitational field. The connection appears to be immediate, a ghostly correlation that transcends the vast distance between them. This was the heart of the EPR paradox, named for Einstein, Podolsky, and Rosen, who used this thought experiment to argue that quantum mechanics must be an incomplete theory. Einstein famously called it spooky action at a distance, a phrase that perfectly captures the profound unease this phenomenon causes. How can reality be structured so that an event here can dictate an event there without any time for communication, seemingly violating the causal structure so carefully laid out by relativity? The resolution, as bizarre as the paradox itself, is that the entangled particles are not two separate objects with hidden instructions. In a very real sense, they are parts of a single quantum system, a unified state that exists as one entity regardless of the spatial separation we perceive. When you measure one, you are not sending a message to the other. You are simply revealing a property of the whole system that was defined the moment the particles became entangled. It forces us to reconsider the nature of reality and locality. Perhaps the fundamental building blocks of the universe are not discrete points in space, but deeper, non-local connections that weave the cosmos into a single, interconnected whole. The space-time fabric we navigate might be a secondary layer, a classical stage that emerges from a far stranger, deeply entangled quantum reality beneath. The strange non-locality of entangled particles hints that the space we perceive might be a kind of illusion. This idea finds its most radical expression in the holographic principle, a concept so profound it suggests our three-dimensional reality might be a projection from a two-dimensional surface. The origins of this principle lie in the thermodynamics of black holes. When matter falls into a black hole, it vanishes behind the event horizon, seemingly destroying all information about it. This presented a paradox, as quantum mechanics states that information can never be truly lost. Physicists, including Stephen Hawking, wrestled with this, and a remarkable solution emerged. They discovered that the maximum amount of information a region of space can contain is not proportional to its volume, but to the area of its surface boundary. A black hole's entropy, which is a measure of its hidden information, is precisely encoded on its two-dimensional event horizon. The entire three-dimensional interior of the black hole, with all its collapsed stars and swirling forces, is completely described by the quantum bits, the ones and zeros, painted onto its spherical surface. This is exactly how a hologram works. A common security hologram on a credit card is a two-dimensional surface, a piece of film with a seemingly random pattern of lines. But when you shine a laser through it, a full three-dimensional image appears in the air. The flat surface contains all the information needed to reconstruct the depth, shape, and parallax of the object. The holographic principle boldly applies this logic to the entire universe. It suggests that the space you are sitting in right now, with its height, width, and depth, might be a magnificent projection. All the information that makes up you, your surroundings, and the distant stars could be encoded on a vast, distant, two-dimensional surface at the edge of the observable cosmos. We are not living inside the universe, we are living inside its shadow, a cosmic illusion generated from a lower dimensional reality. This is not to say that reality is not real, but that its true nature might be fundamentally different from our direct experience. The solid, three-dimensional world feels tangible, but its ultimate blueprint could be written on a flat sheet, a cosmic canvas where the entire story of our universe is stored. If a black hole is a cosmic drain from which nothing returns, then its theoretical twin is a cosmic fountain. This hypothetical object is known as a white hole, and it represents a perfect time reversal of a black hole's behavior. Where a black hole's event horizon is a one-way entrance, a white hole's horizon would be a one-way exit. Nothing from the outside universe could ever cross in, while matter and energy could only erupt outward. The mathematics of general relativity, in their pure time-symmetric form, do not distinguish between past and future. If you take the equations for a black hole and literally run the clock backward, you arrive at the solution for a white hole. It is a region of space-time that is perpetually exploding, refusing to accept anything from the rest of the cosmos. Imagine trying to row a boat toward a powerful waterfall that is flowing uphill, pushing you away with impossible force no matter how hard you struggle. That is the gravitational defiance of a white hole. For a brief moment, some cosmologists wondered if the Big Bang itself could have been a white hole event, the ultimate outburst that spawned our universe. Others speculated that a white hole could be the other end of a black hole wormhole, a place where everything swallowed by a black hole is vomited out into another region of space or time. This idea offers a tantalizing escape from the terrifying finality of the singularity. Yet for all their mathematical elegance, white holes are almost certainly not real. Our universe has a strong preference for increasing disorder, a one-way street defined by the arrow of time. A white hole, which would essentially be a source of perfect order, violates this fundamental thermodynamic rule. It would be like a shattered glass spontaneously reassembling itself, a process so statistically improbable that it is effectively forbidden. Furthermore, any white hole that somehow formed would be incredibly unstable. The moment a single speck of dust, a single photon of light from the outside universe, tried to fall in, the entire structure would theoretically collapse back into a black hole. So while they remain a fascinating ghost in the machine of Einstein's equations, a testament to the strange symmetry hidden within the laws of physics, white holes are likely just mathematical phantoms. They show us what the universe could be if time ran backward, a reflection in a mirror we can never step through. Our own universe may be just one island in an endless cosmic archipelago. The theory of eternal inflation paints a picture of a reality far grander than our observable cosmos, where the Big Bang was not a unique beginning but a local event within a much vaster, eternally expanding meta-universe. In this scenario, what we call the Big Bang was the moment our own pocket of space-time underwent a rapid phase transition, cooling down from an incredibly high energy state to form the stable universe we recognize. But outside our bubble, the inflationary energy field continues to drive an exponential expansion, creating new space far faster than bubbles like ours can form. Within that endlessly stretching background, countless other bubbles are constantly nucleating, each one a separate universe with its own random set of physical constants. In one bubble, the strength of gravity might be 1,000 times stronger, instantly collapsing any structure. In another, the nuclear forces might be too weak to ever form atoms. We simply live in one of the rare bubbles where the numbers allowed for galaxies, stars, and life to emerge. These separate space-time realms are likely forever disconnected from our own. The space between our bubble and its neighbors is expanding at speeds far greater than light, creating an insurmountable barrier. Even if you could travel forever, you would never reach the boundary of another universe because the new space being generated in the gap would outpace any possible journey. This means the multiverse is not a place you can ever visit or observe directly. Its existence is inferred from the mathematics of cosmology and the strange fine-tuning of our own physical laws. We are left to wonder if every possible reality is playing out somewhere in this infinite foam of universes, each one a self-contained experiment with its own unique version of space and time. Even the most perfect crystal seems frozen when viewed in its lowest energy state, but a new form of matter defies this fundamental expectation. Time crystals are not science fiction. They are a newly confirmed phase of matter that pulsates in its ground state, achieving perpetual motion without consuming any energy. Think of a standard crystal like a diamond. Its atoms are arranged in a repeating pattern in space, a symmetry that defines its structure. A time crystal adds a breathtaking new dimension to this order. Its structure repeats not only in space but also in time, oscillating at a constant, locked-in period forever, even when it should be completely still and featureless. This breaks what physicists call time-translation symmetry, the idea that the laws of physics are the same at every moment. For a time crystal, one moment is not identical to the next. Its internal pattern flips back and forth with a rhythm all its own. The creation of the first time crystals involved complex systems, like a chain of ions or a dense lattice of spinning atoms, carefully manipulated and isolated from their environment. When nudged, they don't just settle back down, they begin to tick like a clock that never winds down, a heartbeat woven into the fabric of matter itself. This isn't a violation of thermodynamics, as no work is being done and no energy is lost, but it is a profound challenge to our conventional understanding of equilibrium. What does it mean for our understanding of time if matter itself can have a preferred, ticking rhythm in its most dormant state? These bizarre systems are more than a laboratory curiosity. They hint that time may not be a featureless background, but could have a granular, rhythmic structure that certain forms of matter can latch onto. This rhythmic ticking of matter leads us to the greatest numerical mismatch in all of science, a problem so severe it is known as the vacuum catastrophe. The void of space is not truly empty. It is filled with a seething ocean of virtual particles flickering in and out of existence, a phenomenon we call quantum fluctuations. When physicists calculate the combined energy of all these fleeting particles, the result is a number of such staggering magnitude it defies comprehension. The theoretical energy density of the vacuum should be around 120 orders of magnitude greater than what we actually observe. To put that incomprehensible number into perspective, the difference between the prediction and reality is greater than the difference in scale between a single proton and the entire observable universe. This is not a small error, it is the most colossal failure of prediction in the history of physics. The universe, by all our best calculations, should be tearing itself apart with unimaginable violence, yet it is not. The force of this vacuum energy, if it were as powerful as quantum field theory suggests, would have caused the cosmos to expand so rapidly that not a single star, planet, or atom could have ever formed. The fact that we exist at all is a profound paradox. This staggering mismatch is directly tied to the mysterious force we call dark energy, the repulsive pressure causing the universe's expansion to accelerate. In Einstein's equations, this energy is represented by the cosmological constant, a term he originally introduced to keep the universe static and later called his greatest blunder. We now know the cosmological constant is real, but its observed value is infinitesimally small, almost but not quite zero. Why is the energy of empty space so much weaker than it should be? Why does our universe possess this exquisitely fine-tuned balance that allows for our existence? This is the cosmological constant problem, and it suggests we are missing something fundamental about the very nature of space-time. Perhaps the frenetic energy of the quantum foam is somehow cancelled out by an unknown symmetry of nature. Or maybe our vacuum is just one of countless possibilities in a vast multiverse, and we simply inhabit the rare bubble where the numbers permit life. For now, the vacuum catastrophe stands as a silent monument to our ignorance, a glaring clue that the deepest layers of reality still hold their secrets close. That same cosmic fabric, so rigid in its speed limits, might also contain the secret to bending the rules. The Alcubierre drive offers a breathtaking loophole, a way to travel between stars without ever breaking the universal speed limit locally. Imagine a surfer riding a wave towards the shore. The surfer themselves is not moving through the water with incredible speed, they are carried forward by the wave's motion. The Alcubierre drive applies this principle to space-time itself. A spacecraft would sit inside a region of flat space, a stable warp bubble. In front of the ship, the fabric of space-time would be massively compressed, pulling the destination closer. Behind the ship, space-time would be dramatically expanded, pushing the starting point far away. The ship itself, inside its protective bubble, would be motionless relative to its local space. It would not be accelerating through space, it would be riding a wave of distorted geometry. This means the ship and its crew would not experience the crushing effects of acceleration or the bizarre time dilation that comes with near-light speed travel. You could theoretically cross the galaxy in a matter of weeks, all while the clock inside your cabin ticks at the same rate as a clock back on Earth. The mathematics behind this idea, proposed by physicist Miguel Alcubierre, are perfectly consistent with Einstein's field equations. It is not magic, it is a potential application of general relativity's most profound insight that space-time is dynamic and malleable. However, turning this mathematical elegance into a working engine presents challenges of almost unimaginable scale. The energy required to create and sustain such a warp bubble is astronomical. Early calculations suggested you would need the equivalent of Jupiter's entire mass converted into pure energy, a requirement that placed the concept firmly in the realm of science fiction. Later refinements have hinted that the energy needs could be lowered, perhaps to the mass of a small moon, but this is still far beyond our capabilities. The greater obstacle may be the type of matter required. To shape space-time in this way, you would need what physicists call exotic matter. This is not antimatter or dark matter. Exotic matter would have to possess negative energy density, something that pushes space apart rather than pulling it together. While quantum field theory allows for the existence of negative energy in tiny amounts, like in the Casimir effect, creating the vast quantities needed for a warp drive is a completely different problem. For now, the Alcubierre drive remains a beautiful thought experiment, a glimpse of a future where we might not punch through the universe's speed limit, but instead cleverly reshape the road ahead. It stands as a testament to human ingenuity, proving that even the most rigid laws of physics can be navigated with a little creative bending. The final astonishing fact brings us from the cosmic scale to the intimate world within our own minds. Our direct experience of time as a flowing river with a definite past and an open future may be the most persistent illusion of all. Physics describes a universe where time is just another dimension in a static block, but your consciousness insists on a narrative, a relentless stream of now. How does the human brain generate this powerful sensation? Neuroscientists suggest it is a sophisticated trick of perception, a way for the brain to organize a chaotic influx of sensory data into a coherent story. Your mind is not a passive recorder of a flowing present. It is an active editor, stitching together moments with a slight delay to create a seamless timeline. Think about the last time you heard a loud, unexpected sound. Your brain actually backdates the event, making you perceive the sound as having happened at the moment your eyes registered the source, even though the processing took extra milliseconds. This editing creates the smooth, linear experience you take for granted. This subjective time is incredibly flexible, a stark contrast to the rigid ticks of an atomic clock. Time seems to crawl during a boring lecture, yet it flies by in a moment of terror or joy. Your personal timeline is not a universal constant. It is a psychological construct shaped by emotion, attention, and novelty. So where does this leave us? We are caught between two irreconcilable truths. The universe, in its objective reality, may be a timeless block where all moments persist equally. Yet our conscious awareness paints a different picture, one of passage, memory, and anticipation. This is the ultimate mystery of space-time. Is the flow of time a fundamental property of the cosmos that we are only partially perceiving? Or is it a story our brains tell themselves to make sense of a reality where past, present, and future are already written? Perhaps consciousness is not just a passenger riding the arrow of time, but the very faculty that draws the arrow in the first place. This internal clock of yours is a symphony conducted by your brain. Deep within your hypothalamus, a tiny cluster of neurons called the suprachiasmatic nucleus acts as the master conductor, synchronizing your body's rhythms with the 24-hour cycle of daylight and darkness. This is your circadian clock, setting the tempo for sleep and wakefulness, but for measuring shorter intervals, the seconds and minutes of a waiting room or a thrilling movie, your brain relies on a different mechanism. One leading theory suggests a structure called the basal ganglia, along with the neurotransmitter dopamine, creates a pacemaker accumulator system. Think of it as a neurological metronome ticking at a steady rate, with each tick representing a pulse. When you need to judge a duration, your brain starts counting these pulses. The number of pulses accumulated equals your perceived length of time. This is why your sense of time is so fluid. During a surge of adrenaline or intense focus, your internal metronome speeds up, causing it to generate more pulses for the same objective period. When you recall the event, your brain looks at that high pulse count and concludes that a long time must have passed, making the car crash feel like it unfolded in slow motion. Conversely, when you are bored or drowsy, the metronome slows, fewer pulses are counted, and time seems to contract. Neurological conditions can profoundly disrupt this delicate system. Parkinson's disease, which involves a depletion of dopamine in the basal ganglia, often causes patients to severely underestimate time intervals, as their internal clock is literally losing ticks. Your experience of time's flow is not a single process but a fragile construction, a consensus reached by different brain regions interpreting rhythms, emotions, and memories. So the next time an hour flies by or a minute drags on, remember that you are not just watching the clock, you are the clock, a living instrument whose tempo is constantly being rewritten by your own biology. We have traveled from the warping of gravity to the final frontiers of your own mind, uncovering a reality where time is elastic and space is alive. These 30 glimpses reveal a cosmos that is not a cold, empty void, but a dynamic and deeply interconnected fabric, a single entity of breathtaking complexity where black holes spin space into whirlpools and the vacuum itself seethes with potential. This journey challenges everything we assume about our everyday experience. The solid ground beneath your feet, the steady tick of a clock, the very flow of your thoughts, all are part of a grander, stranger geometry. While we may never perceive this hidden tapestry directly, its effects are woven into the technology we use, the stars we see, and the time we feel passing. Our exploration proves that the universe is far more wondrous and bizarre than our limited senses can ever convey. If your perception of reality has been bent and stretched by these cosmic truths, let us know. Share your thoughts in the comments below. Tell us which fact reshaped your understanding. And if you are ready for more journeys to the edge of physics, subscribe for further adventures into the unknown.